This topic will cover how to find the volume of revolution formed when a curve is rotated around the x-axis or the y-axis. In 2 dimensions, we can work out the area under a line or a curve, either by integration or simply by calculating it. For example, this rectangle has an area of 8. In 3 dimensions, this area could be rotated 360 degrees around the x-axis to give us a volume of revolution. As we can see, the shape formed is a cylinder. We can calculate its volume using the formula for the volume of a cylinder, which is the area of the circle, pi r squared, multiplied by the length of the cylinder. So in this case, we would get pi multiplied by 2 squared multiplied by 4, or 16 pi. Notice that the 2 is the radius of the circle, and this is also the y-coordinate of the original rectangle. With more complicated areas, we can estimate the area under a curve by splitting it into a series of rectangles to give an approximation for the area under the curve. In this case, you can see that we've split the interval from x is 0 to x is 4 into 4 rectangles, so each rectangle has a width of 1. Each rectangle also has a height, which could be found by substituting the left x-coordinate of that rectangle into the equation of curve. So for example, the first rectangle could be found by substituting x equals 0 into x squared plus 5. The height of the second rectangle could be found by substituting x equals 1 into x squared plus 5, and so on. So if we were to rotate this area about the x-axis 360 degrees, we would also get an estimate for the volume of revolution for the curve y equals x squared plus 5. So that volume can be found by finding the volume of each cylinder separately and adding them together. So the first cylinder would have a volume of pi r squared h. So in this case, r is the y-coordinate of the first rectangle. H is going to be 1 because that is the width of each rectangle in this case. The second would again be pi r squared h using x equals 1 to find the r value. The third rectangle and the fourth rectangle. So we can simplify this, factorising out pi to give us 338 pi as the volume. If we had taken this volume calculation and factorised before we had calculated the value, we would have seen that we could have pulled out a factor of pi and also a factor of 1 from each of the volumes. Then what is left in the middle is the sum of all of the y values of each cylinder squared. So what we have is pi multiplied by, and this represents the sum of each of the y values squared, each of the cylinders, starting with the cylinder where x equals 0 was used, and finishing when we get to the cylinder where x equals 3 was used. This is then multiplied by 1, that is the thickness of each of the cylinders. So this could be written as pi multiplied by the sum of y squared, starting from x is 0 and finishing x is 3, multiplied by 1. If we wanted to improve this estimation, we could reduce the thickness of each cylinder and increase the number of cylinders. So by taking more cylinders in other words, splitting the original area into more rectangles, we would find a better estimate for the area and therefore the volume of revolution. So going back to the original curve, if we were to use thinner rectangles, you can see that the rectangles better fit the area we're trying to estimate. This would translate to more cylinders in the volume of revolution. So the formula for this volume of revolution, for this estimate, this time using the same idea of adding up the volumes of all of the individual cylinders and factorising out any common terms, we can see that we will get pi multiplied by the sum of each of the y² values multiplied by the thickness of each cylinder, which this time is only 0.5 because we've got thinner cylinders. We'll be looking at this idea of using a summation in second year maths. So to get a very accurate volume, we will need a lot of cylinders. In this case, the cylinders will have a very small width, and we use the symbol delta for that. So delta x is the width of each cylinder, and it just represents a very small value of x. So in this case, the formula that we have for the volume of revolution formed is pi multiplied by some of the y² values multiplied by delta x, and we are allowing delta x to tend towards 0. This means that the width of each cylinder is getting smaller and smaller, close to 0, or in other words, the area that we are covering is becoming closer and closer to the actual area rather than individual rectangles. This is known as a limiting process. In this case, we're going to use a and b as the limits of x, so the values of x of each side of the area covered. Now, as delta x tends towards 0, this sum of discrete cylinders is going to become an integral. It's going to be a smooth, continuous function. So in 2 dimensions, this represents the area under the curve. In 3 dimensions, this becomes the volume of revolution. So the formula becomes pi multiplied by the integral of y². Now a and b become the limits of the integral. And the small change in x, delta x, becomes the dx part of the integral in the limit. So we can now find the volume of revolution formed when the region bound between the curve y equals x² plus 5, x equals 0, x equals 4, and the x-axis is rotated around the x-axis. We want to find this volume and then give the answer to 3 significant figures. So because we're rotating around the x-axis, the formula we're going to use is this, pi multiplied by the integral of y² dx, with a and b being the x values. So this is going to become pi multiplied by the integral from 0 to 4 of x² plus 5 squared. This is because y is x² plus 5. So in order to do this integral, we need to first expand the brackets. We can then integrate the function and evaluate it between 0 and 4. Now, expanding this, we've been asked to give the answer to 3 significant figures rather than in an exact form. So instead of leaving it as a multiple of pi, we're going to work out the answer. It actually comes to 1627.76. So to 3 significant figures, that becomes 1630. If you were asked to give it as an exact value, you would calculate it and leave it as a multiple of pi. Volume of revolution can also be found by rotating a curve around the y-axis, and this will give a different volume to the rotation around the x-axis. The formula for rotating around the y-axis is given here, pi multiplied by the integral of x squared dy, and this time the limits need to be the y values. So a and b are both values of y in this case. So for example, if we wanted to find the region bound by y equals x squared plus 5, y equals 6 and y equals 10 around the y-axis, we would use the formula pi times the integral of x squared dy. So first of all, we need to find an expression for x squared in terms of y. So we need to rearrange the formula for y equals x squared plus 5 to give us x squared equals y minus 5. That is going to be the function that will be integrated. We already have y values, we have 6 and 10, so they become the limits here. If we'd been given x values, we would have needed to substitute those into the function for y in order to get y values to put on the integral. We can now integrate with respect to y. Which gives us, to three significant figures, 37.7. So the volume of revolution of a solid formed when rotating a curve around the x-axis can be calculated using this formula. And a volume of revolution for rotating around the y-axis can be calculated using this formula. Notice that the limits need to be x for the rotation around the x-axis and y for the rotation around the y-axis. Pause the slide now and calculate this volume of revolution. So we're looking for the volume of revolution around the x-axis. So the formula we're going to use will be the integral of y squared dx multiplied by pi from 0 to 3. So y is the square root of x squared plus 1. That means that y squared will be x squared plus 1. So the integral becomes the integral of x squared plus 1 from x is 0 to 3. So this gives us a third x cubed plus x between 0 and 3. This becomes a third of 3 cubed plus 3 minus, then f of 0 is just 0. So here we get pi multiplied by a third of 27 plus 3. This gives us 9 plus 3 pi, so 12 pi. Now pause the slide and calculate this volume of revolution about the y-axis. So because we're rotating around the y-axis, the formula we're going to use will be pi times the integral of x squared dy. We're going to need to find the interval that we're integrating over in terms of y as well. So because x is going from 1 to 4, y will be 1 over 1 and 1 over 4. So we're going to be integrating on the integral interval between a quarter and 1. So because we're just interested in that interval, we're actually going to swap it over so that the smallest number is on the bottom. We also need to find an expression for x squared. So x will be 1 over y. So x squared will be 1 over y squared. So the integral becomes the integral of 1 over y squared dy on the interval from 1/4 up to 1. So to integrate this, we need to rewrite 1 over y squared as y to the power minus 2 so that we can do the integral. This gives us minus y to the power minus 1 or minus 1 over y. So in order to calculate this, first going to find f of 1. And then f of 1/4. So the answer we get is 3 pi. Now complete the questions in exercise 10A on page 227.